Welcome back to our next section. This is Dr. Tullis. We are going to describe the collision theory of reaction rates and use collision theory to describe the effects of reactant concentration, molecular orientation, and temperature on a reaction rate. We're going to look at activation energy and how that relates to the rate of a reaction. We're going to understand reaction coordinate diagrams and use the Arrhenius equation to calculate the activation energy from rate constants at different temperatures. Chemists often turn to the particulate level of chemistry to explain chemical phenomena. Looking at the way reactions occur at the atomic and molecular levels can give some insight into the various influences on the rates of reactions. Let's review the macroscopic observations we have made so far concerning reaction rates. There are wide differences in rates of reactions, from very fast reactions like the explosion that occurs when hydrogen and oxygen are exposed to a spark or a flame, to really slow reactions like the formation of rust that occurs over days, weeks, or even years. For a specific reaction, factors that influence reaction rates include the concentration of the reactants, the temperature of the system, and the presence of catalysts. Each of these influences can be explained using the collision theory of reaction rates, which states that three conditions must be met for a reaction to occur. The first, the reacting molecules must collide with one another. Molecules that are moving too slowly with too little of kinetic energy don't react when they collide. Reactants have to bombard one another to break bonds in order for them to rearrange and form the new products. The reacting molecules must collide with sufficient energy to initiate that process of breaking and forming bonds. Bond breakage requires energy. To break a bond, it requires energy. Think about if one of my reactants was, let's just say, H bonded to Cl. In order to create the products, let's say I want H2 and Cl2, I need to break this bond. Think about snapping a twig. You have to put force in, put energy in to break that bond. And three, the molecules must collide in an orientation that can lead to rearrangement of the atoms and the formation of products. We know that rate constants vary with temperature, so the actual rate of a reaction is very temperature dependent. Why the rate depends on temperature can be explained by collision theory. Collision theory assumes that for a reaction to occur, reactant molecules must collide with sufficient energy in the proper orientation. We just said that. In a lab or in the chemical industry, a chemical reaction is often carried out at higher temperatures because it allows that reaction to occur more rapidly. Those people that are observing these reactions in the lab or in the chemical industry are on a timeline. So they want to make these reactions happen in minutes, hours, or days, not years. So we want them to happen rapidly. But sometimes it is desirable to lower the temperature to slow down a chemical reaction to avoid any uncontrollable reactions or a dangerous explosion. Reactions are faster at a higher temperature because a larger fraction of reactant molecules have enough energy to convert to product molecules. If the activation energy is low, a high portion of the molecules in a sample might have enough sufficient energy to react. The reaction will be fast. If the activation energy is high, only a few reactant molecules in a sample might have enough energy, and the reaction will be slow. We can see here on this graph that the energy increases as I go to the right. So down here is lower energy, which means lower temperature. Lower temperature is lower energy. Higher energy, higher temperature. And if this is our minimum energy required to react, at the higher temperature there will be more reactions happening at that higher temperature than at this lower temperature. Activation energy is that minimum energy that's required to initiate a chemical reaction. It's specific to a particular reaction. Let's look at this guy down here. We have NO2 and CO as our reactants. Here's our reactants. we want this reaction to occur and create these products, NO and CO2. Well, in order for that to happen, there's a certain amount of energy that must be met. This is my activation energy. This difference to go from reactants up to the top here, and in this case, EA activation energy is 132 kilojoules per mole. That is the amount of energy needed to go from reactants to make this reaction happen. The top part here is called our activated complex. That is our minimum kinetic energy that reactant molecules must have to be converted to product molecules. Now, if I wanted to go in the reverse direction, if I wanted my products to be turned back into reactants, notice here that I have EA prime. This is going in the opposite direction. I would need to go up to here. This difference right here would be the energy needed to make it go backwards, 358 kilojoules. There's two different types of reactions. There's an endothermic reaction, and that is when the forward activation energy is pretty great. And the delta H we can see here is a positive value. So going from reactants to products, we can see this activation energy is 85 kilojoules per mole. The opposite direction is only 2 kilojoules per mole. But going forward and going from reactants to products, the difference between where the reactants are and the products are not going up to the top, but this part, this delta H, is a positive value, as opposed to an exothermic reaction shows that the products are more stable than the reactants. The products are at a lower energy. Here's my reactants, here's my products, and to get from reactants to products, that delta H is a negative value. Going from reactants up to my activated complex, this activation energy is going to be less than the reverse activation energy. That would be an exothermic reaction. So not only must reacting molecules have sufficient energy to react, but the reactant molecules must also come together in the correct orientation. The lower the probability of achieving the proper alignment, the smaller the value of K, and the slower the reaction. Imagine what happens when two or more complicated molecules collide. In only a small fraction of the collisions will the molecules come together in exactly the right orientation. So, only a tiny fraction of the collisions can be effective. No wonder some reactions are slow. Conversely, it's amazing that so many are fast. This brings us to the next topic, which is our Arrhenius equation. The Arrhenius equation connects the observation that reaction rates depend on the energy and the frequency of collisions between reacting molecules, on the temperature, and on whether the collisions have the correct geometry. Molecules must be given enough energy to become activated before they can react. Here we have an equation here. K is equal to AE raised to the negative activation energy over RT. What do all these mean? K is our rate constant. You've seen that before. A, this is a new variable. It's our frequency factor constant, and it's related to the number of collisions and the fraction of collisions that have the correct geometry. E is the base of natural logarithms. EA is our activation energy. R, you've seen this, is our gas constant. And temperature is always in Kelvin. A few things about this Arrhenius equation. The exponential term gives the fraction of molecules having sufficient energy for reaction and is a function of temperature. Although a complete understanding of the frequency factor goes beyond what we will cover in this Gen Chem 2 class, note that A becomes smaller as the reactants become larger. This reflects the fact that larger molecules have a smaller probability of coming together in the appropriate geometry. The factor that's E raised to the negative EA over RT always has a value less than 1 and represents the fraction of molecules having the minimum energy. This fraction changes significantly with temperature. The Arrhenius equation is significant because it can be used to calculate the activation energy. It can also be used to calculate the rate constant if activation energy, temperature, and A are known. Let's rearrange this equation in logarithmic form. If we take the natural log on both sides, we get this equation. And we can relate this to our y equals mx plus b format to give us a straight line. Notice that our y is the natural log of k right here. And our x, this is our x is 1 over temperature. That will give us a straight line. And our slope, the m, our slope is negative EA over R. All of this is on your cheat sheet. Let's look at a sample problem. Using the experimental data in the table below, calculate the activation energy for this reaction. So in 4 different experiments, we were given the temperatures for those trials, and we found the rate constant for each of those 4 trials. How can I find the activation energy? According to that data, we were given rate constants at several different temperatures. Now to solve this graphically, we need the natural log of K and we need 1 over temperature. Because we saw that in our cheat sheet here, the natural log of K is my y-axis, my x-axis is 1 over temperature. I was given K and I was given temperature, so let's get the natural log of K and let's get 1 over temperature so that we can plug it into an Excel spreadsheet. All I did was take my temperature, my 1125, and I did 1 divided by 1125. And I got 8.88 times 10 to the negative 4th. So I have a new column that I made here with my 1 over temperature. So I did that for all 4. I was given K values. So the first K value was 11.59. So I made another column here. So I did the natural log of 11.59, 2.4501. So I made another column of my natural log of K and a column of my 1 over temperature. And I did that for each of those trials. Then I got into an Excel spreadsheet and I entered in this data and this data. I had my X and my Y axes and it plotted it for me. When it plotted it, I right-clicked on those data points and I had it made me a line of best fit. And it gave me an equation in y equals mx plus b format. The m is your slope. And when I got that m in Excel, it gave me this value, negative 3.03 times 10 to the 4th. That's my slope. Well, slope is equal to negative EA, activation energy, over R. We know that from this. So I can say that that negative 3.03 times 10 to the 4th is equal to negative EA over R. We know R, our gas law constant, is 8.31 times 10 to the negative 3 kilojoules per mole Kelvin. Now my only unknown variable is the activation energy. So I'm going to multiply negative 3.03 times 10 to the 4th times negative 8.31 times 10 to the negative 3. Multiply those together and I get my activation energy. I rounded to 2 significant figures. So 250 kilojoules per mole. Our next sample problem, we're told that rate constants were determined for the decomposition of acetaldehyde in the temperature range 700 to 1000 Kelvin. Use this data to determine the activation energy for the reaction using a graphical method. I'm given temperature and I'm given rate constants at 1, 2, 3, 4 different time periods. Let's do the same thing we just did for this last one. Similar to the last one, I took my temperature and I made a new column of 1 over temperature. So I was told that my first temperature was 700 Kelvin. So I made my next column 1 divided by 700 and I put in 0.001429. That's what that came from. I did 1 divided by 760 to get that. 1 divided by 840, 1 divided by 1000. I was given the rate constants for each of those 4. So the next one, I took the natural log of each of those k's and I made a new column. So I have my x-axis, I have my y-axis. I put those into Excel and I asked for the line of best fit, and it gave me y equals mx plus b. It gave me my slope, negative 22336. That's what I'm going to plug into. My slope is equal to negative EA over R. I then rearrange this for you instead of writing it all in, because we know if I cross multiply, slope times R is equal to negative EA times 1. EA is equal to negative R times the slope, and when I do that, I got 185.7, and I went to two significant figures for 190 kilojoules per mole. That would be my activation energy for the decomposition of acetaldehyde. It would be great if we could solve for activation energy algebraically instead of graphically. So we found that there is a way mathematically to do it. The activation energy for a reaction can be obtained algebraically if K, the rate constant, is known at two different temperatures. So if we know two different rate constants and two different temperatures of those rate constants, we were able to combine two equations, and we eliminate the natural log of A by subtracting the two to get this. This is also on your cheat sheet. With this form of the equation, given the activation energy and the rate constant at a given temperature, we can find either the second rate constant, or we could find the other temperature if we were given one of the two. For example, let's use the values of K determined at two different temperatures to calculate the value of the activation energy for the decomposition of HI. Let's work through it together. I'm going to use this version of the Arrhenius equation to solve, taking the natural log of K2 divided by K1. So I took the K2 value, the 2.39 times 10 to the negative 7, that's my K2, divided by my K1 is equal to negative EA over my R, and my R is given to us here. We can either use 8.31 joules, or we can use 8.31 times 10 to the negative 3 kilojoules. I've just been using the kilojoules just because the activation energy would get very large if you're not using kilojoules. And then I times it by 1 over T2 minus 1 over T1. Let's work through this algebra together because I know it can be kind of intimidating. I simplified my natural log on the left. I took the natural log of 2.39 times 10 to the negative 7 divided by 2.15 times 10 to the negative 8. Hit that parenthesis, and I got 2.4084. That was my answer on the left. I brought down my negative EA over R and times it by. I did the temperature and I simplified my temperature. So I took in parentheses 1 divided by 700, close that parenthesis, and I minused 1 divided by 650 parenthesis. And I got negative 1.0989 times 10 to the negative 4th. So I brought that down. Then I wanted to simplify this even further. I wanted to get rid of this denominator. So to get rid of a denominator, multiply it by itself. So that would cross it off. If I multiply it on the right, I have to multiply it on the left. So I took my 8.314 times 10 to the negative 3, because that's in kilojoules, and I timesed it by 2.4084. So on the left now, I have 0.0200234 is now equal to negative EA times what I got for my temperature. To get EA by itself, I need to divide by that negative 1.09 times 10 to the 4th, so I have to do it on both sides. So take this answer that I got on the left, divide it by negative 1.0989 times 10 to the negative 4th, I got negative 182. Negative 182 is equal to negative EA, so divide both sides by that negative, and I got 182.2. I went to two significant figures, so 180 kilojoules per mole. This is our last sample problem. We have the colorless gas N2O4 decomposes to the brown gas NO2 in a first order reaction. We're told the rate constant at the temperature of 274, and we're told a rate constant at 283. What is the activation energy? Let's figure that out. Because I was given two different rate constants and two different temperatures, we're using our Arrhenius equations to solve for the activation energy. I set it up the same way as I did the last one, where I took K2 over K1. I used my R value, the kilojoule one. You could use it in joules if you want. You're just going to get 3 extra zeros on the end. I took my second temperature, the 283, minus the 274. Make sure you keep the K1 and the T1 together and the K2 and the T2 together. I did the same thing where I simplified. I took the natural log of that divided by that, and I got 0.798508. I'm not going to do any rounding until the very end. So make sure, plug this into your calculator. Make sure that you get the same thing that I do. I did my temperature simplification. So I did 1 over 283 minus 1 over 274. And this was the answer I got for that. I got rid of my denominator by multiplying it by both sides. That gave me this on the left. And then I divided both sides by what I got for my temperature answer to get my activation energy at 57 kilojoules per mole. And that wraps up this section.